So this is the second part of chapter 11. So I've talked about how oligodendrocytes and Schwann cells are the one responsible for the myelination of the axon, which helps to increase conduction. It helps with propagation of action potential. Now, you see how the myelin, which I told you is white color, wrap around the axon. Now, you notice that there are some gaps on the axon that are not myelinated. Now, those gaps, we call it the nodes. All right, so the gaps where there's no myelin, we call it nodes. Now, it's called node of Ranvier. See that? Is a gap between myelin sheets. So we call this myelin sheet on the axon. So the portion on the axon that are not myelinated is where we call node of Ranvier. The portion of the axon that is not or that are not myelinated, node of Ranvier. All right. Now, oligodendrocytes. Okay, we've talked about that. Now, demyelination is when the myelin is removed. All right. Demyelination is when there's loss of myelin sheath. Now, this could result from result in abnormal function of the neuron. And you want to think about it. If this black cable now is peeled off, or what you notice that happens most of the time to your power cable is if the edge begins to peel, what's going to happen? The charger also will start, the power cable will start to malfunction over time. So that is actually what happened when the myelin is removed. It affects the conductivity power, the propagation power of the axon, and that happens in multiple sclerosis. Now, we want to look at the nervous system, and the gray matter and the white matter of the nervous system. Now, I told you earlier that axons are myelinated, and the portion of the axon that are myelinated has myelin. That's what that means. And that part that have myelin is white. All right. So if myelin is white, that means there will be some part of the cell that is white. So that portion, we call it white matter. So when we are studying spinal cord now, for some of you that are already there in your lab, when you are looking at the spinal cord in the lab, you will see that there are some portion of the spinal cord that is called white matter. And they say there is one that looks like there are some part that look like H. You remember? That is gray matter. So the reason we call a portion white matter is simply because of myelin. All right. So you expect that since it's only axon that is myelinated, that means the only part of the white matter will be axon. So the myelinated axon as only part of the portion that makes the white matter. Then you remember the other time I told you that nucleus body, which is where we have the rough endoplasmic reticulum, is gray in color, is gray in appearance. So every other part of the myelin, every other part of the neuron that is not the myelinated axon is what we call the gray matter. So unmyelinated axon, like the node of Ranvier, every portion of the axon that is not myelinated rather is the gray matter. The cell body, gray matter. The dendrite constituted gray matter. Axon terminal, they don't have myelin there, constituted gray matter. And the neuroglial cells that are not myelinated as well, obviously, constitute gray matter. So this color, the gray matter, is due to the nucleus body, which is what constitutes the RER, rough endoplasmic reticulum. So when you're looking at the brain outer cortex, you see gray matter there. When you're looking at the spinal cord, on the outside of the spinal cord, you have white matter, which is made up of myelinated axon. And the central H, there's an H on the spinal cord that is the gray matter, which I will still show you when we get to that point. Now, nucleus, they are cluster of cell bodies in the central nervous system, and they have gray appearance. They're going to have gray appearance. Why? Because in the nucleus, you have the nucleus body, which is made up of RER, and that RER is gray in appearance. So gray appearance, we call it nucleus, this cluster of cell body rather, in the cell, on the neuron. Now, I will start to talk about action potential now. Now, you must follow me very carefully. It's very interesting and volatile. Now, because you can watch it over and over again, I'll be a little fast. Now, every cell, when it's at rest, we say it has resting membrane potential. What is potential? Charges, volts. All right. So when a cell is at rest, when a neuron is at rest, we say it has resting membrane potential. And on general notes, the neurons we are looking at now, their resting membrane potential is negative 70 millivolts. All right, it's negative 70 millivolts. That's the membrane potential when there's rest. At rest means there's no stimulus at that point. Now, you remember that I told you the other time that when when stimulus are received, they will be processed in the soma, and when they are processed in the soma, the decision, which is the impulse, is going to be deposited in the axon hillock. It will keep depositing in the axon hillock. And I told you that it's not all stimulus that generate an action. So since it's not all stimulus that generate an action, then there will be some stimulus that will initiate a response. I mean, that will generate action as impulse, but the impulse is not enough to cause an action to happen. All right. Now, that point, we say that a graded potential has been initiated. So graded potential. Now, another name for graded potential is localized potential or localized event. Now, the word localized means it is localized to a location. So it is going to be in the axon hillock. It's not going to spread out into the axon to transport it. No, it is just going to be at a location. So that's why we say it is localized. Now, as the impulse is dropped into the axon hillock, there is possibility that it's going to be enough to fire an action potential. If it is enough to fire action potential, then it has fired an action potential. If it is not enough, at that point, we say the threshold was not reached. If the threshold is reached, there is no point, no way that there will not be action potential. Now, so we say that action potential can either be achieved or it may not be achieved, because there's nothing like there was a little action potential. No. If it's a little action potential, then it's a localized event or a graded potential. So we either have graded potential or we have action potential. Graded potential means the stimulus is not enough to push the membrane from its rest to create action potential. It reduces it a little bit, but it does not bring it to the threshold. Now, what do we call threshold? Now, let's say I have this, for instance, now, and I put it on this surface. Let's say I have this here. Let me use this. So I have this here. Can you see me? Let me know if you can see me. Can you look what I'm showing? All right, cool. Now, if I have this marker here, and action potential is for this marker to drop. Now, if this marker is here, it's not dropping. That means, okay, let's start from here. It's not dropping. That means there's graded potential. I applied a little stimulus, it still didn't drop. Action, graded potential. I applied a small stimulus, it still didn't drop. Graded potential. It is localized. There's a stimulus, but it's not enough to cause an action. I applied another stimulus, it still didn't drop. Graded potential. I applied another stimulus, now it looks like it's going to drop. Now, once I apply this stimulus, can I control if it's going to drop or not? Now I can't control it again. It definitely dropped without pushing it. I don't need to control it again. Once a stimulus come into your neuron and it push your neuron to a threshold. Now, the point where this marker dropped is the threshold potential. Is it potential when I can't control it again, it has reached the threshold. And that's the same thing that happens to you when a friend keeps offending you and you said you didn't do anything. The friend did something, you didn't react. The friend did something, you didn't react. And you told yourself that once this friend pushed me to the corner, once he pushed me to the wall, I'm going to react and give it to him. And now, the point when you cannot but react is your threshold. Now, don't react, okay? Now, the point where you cannot but react is your threshold. That's the same thing with your neurons. There's a point where when your potential, the electricity, the voltage of your neuron drops to negative 60, there's nothing you can do again. When your potential, when the membrane potential drop to negative 60, action potential must be fired. If it is on negative 65, that's not the threshold. Negative 68, that's not the threshold. We call all of those localized or graded potential. Does it make sense to you? All right. Okay, cool. So actual potential is the point where the wave, where there is already, the moment where the threshold has been reached. Now, I want to ask you, can there be action potential without reaching the threshold? The answer is no. Once the threshold has been reached, which is negative 60, once that has been reached, then action potential will be fired. So action potential must be fired once a neuron reach the threshold voltage or current. Let's go. Now, if you look at this now very carefully with me, you will see that you will understand what I'm talking about on the voltage and what controls the current. Please look at this carefully with me. So measuring this neuron now, the voltage on this neuron is negative 70 millivolts. Now, at this point, we say that the neuron is in a state of rest. And we say that this is resting membrane potential. Now, what are the characteristics of resting membrane potential? What is the major characteristics of resting membrane potential? At that point, we say the cell is polarized. We say that that cell is polarized. Now, what does that mean? It means that the cell is more negative inside. So it means inside is more negative and outside is more positive. Take note, I didn't just say inside is negative and outside is positive. I use a comparative word. I said inside is more negative than outside. So the issue is that the inside is more negative than the outside. All right. So let your emphasis not just be that on the charges yet. All right. So when the inside is more negative than the outside, we say this membrane or the cell is polarized at that point. So in a state of rest, the inside is usually more negative than the outside. So that means resting membrane potential is a polarized membrane. We'll take that again. A resting membrane potential is a state when the inside of the cell is more negative than the outside. That is being polarized. So when a cell is polarized, we say it is in a resting membrane potential. All right, so the resting membrane potential specific for this neuron is negative 70. Now, we have 3 channels here. Number 1 is the potassium link channel. Potassium by itself, or potassium, has the ability to drive a cell to negative 90 millivolts. Please take note of that somewhere. Potassium has the ability to make a cell to become negative 90 millivolts. No, so I was using an analogy for my student yesterday that some of you are doing chemistry currently and some of you are doing biology. Now, and I told them, the moment I enter your class, what do you think I'm coming to do? I'm simply coming to teach you biology. I'm not coming to teach you chemistry. So the moment you see me, you know I'm coming to drive you towards more knowledge in biology. And the moment you see your chemistry professor, you know he's coming to drive you towards more knowledge in chemistry. All right, so look at this. There's another channel here that we call sodium leak channel. This channel has the capacity to drive a neuron up to positive 30 millivolts. Please take note of this and keep it somewhere. All right. Now, potassium has ability to leak out. It goes out and make a system to become negative 90. Whereas sodium has the ability to come in and make a system to become 30, positive 30 millivolts. So it's like your biology professor, when he comes in, he wants to teach you how to become more biology oriented. But when your chemistry professor comes in, he wants to teach you how to be more chemistry oriented. Now that's the same thing. Anytime that potassium is in charge, the purpose of being in charge is to make a cell to become more up to negative 90. Whereas anytime sodium is in charge, sodium wants to make a cell to become up to positive 30 millivolts. Now let's see how they do their job. Now, those are the two systems there. There's another one system which we call sodium potassium pump. This guy, on the contrary, so potassium goes out through this channel. So potassium goes out through this channel. Sodium comes in through this channel. But through the sodium potassium pump, they go otherwise. So here, potassium comes in through this channel. So potassium, 2 potassium comes in, 2 potassium comes in through this channel, and 3 sodium goes out. 3 sodium ion goes out through this channel. Sorry about that. Now, so again, I talked about 3 components here. Number 1 is the potassium leakage channel, which pumps potassium out. Now, when it's pumping potassium out, when it's in charge, when it's activated, the purpose is that it wants to make this cell to become negative 90 millivolts. All right. Now, there's sodium leakage channel. And the purpose of sodium leakage channel is that sodium comes in. And when sodium is coming in, it wants to make this cell to become positively charged and up to positive 30 millivolts. Now, there's another balancing system in between the two of them. This system pumps both. It pumps potassium in, contrary to the direction of potassium leakage channel. Then it pumps sodium out, contrary to the direction of the sodium channel. All right, 2 potassium goes out, 3 sodium comes in. Now, let's now go ahead and look at this process. If you have understood this, then we are good to go. Now, follow me now very carefully on this process to look at how resting membrane potential works. Now, because the plasma membrane is highly permeable to potassium ion, the resting potential is fairly close to negative 90 millivolts, which is the potential for potassium ion. I told you that potassium has the capacity to drive a system towards becoming itself, which is negative 90 millivolts. Now, although the electrochemical gradient for sodium ion is very large, all right, the membrane's permeability to those ion is very low. Consequently, sodium has only a small effect on normal resting membrane potential, making it just slightly negative than it would be. So what sodium does is just to help it. The system is not getting to negative 90, but it's actually negative 70 because of sodium. Now, the sodium potassium pump ejects 3 sodium out, I told you that earlier, and 2 potassium in. So it goes in ratio 3:2. 3 sodium goes out, 2 potassium comes in. Now, at normal resting membrane potential, this passive and active mechanism are in balance. The membrane potential varies widely within the cell. A typical neuron has negative 70 millivolts. Now, negative 70 millivolts, not up to negative 90, which is the potential for potassium. Let's go. Now, look at what we call graded potential. Look at what we call graded potential now. Now, graded potential again, which I've explained to you, another name for graded potential is localized event. Localized in that it is not propagating. The stimulus is not enough to create an action potential, so it is just localized in a place. Now, see, at rest, this is a cell at rest, negative 70 millivolts. Now, stimulus is now applied. When stimulus is applied, the impulse arrives at the axon lock, but it's not enough to cause an action to happen. So it is just located there as a graded potential or localized event. So see, what has happened here, the membrane has changed to become negative 65. But see, all of these places are still not getting anything. They are still as negative as it was. See, it was all negative here. This portion now has gotten some disturbance, but this part is still undisturbed. The membrane still remains intact at rest. Now, when you get here, it looks like this is getting to become negative 60, which should have been enough to fire an action potential. But see what happened here. This is where the whole process starts. The whole process starts here. So the impact of the stimulus should be high here. But by the time it gets here, this impact did not spread here. It's still negative 65 here. Here is still negative 70. So on the average, the general membrane potential is not negative 60. This portion is negative 60, negative 65, negative 70. So the general membrane potential has not reached the threshold. All right. So at this point, we say the event is just localized. You see, it didn't even get here at all. Everything here is still normal. So we say this has just generated a local event, a local current. It is a graded potential. Now, if the system was enough, if the stimulus was enough to generate action potential, the whole membrane will be disturbed. But here it's just a little part of the membrane that was disturbed. That's not enough. It's a localized event. It's a graded potential. Let's go. I'll go ahead and look at what the description of graded potential is now, the characteristics that you will see when there's graded potential. Now, graded potential, whether it's depolarizing, I'll talk about that. I told you that when a membrane is at rest, it is polarized. So the word depolarized simply means opposite of polarized. So if a membrane is at rest and it is polarized, and there is more negative inside than outside, all right? So come here with me now. Come here with me. Now, I said when a membrane is at rest, it is polarized. Resting membrane potential is polarized. And polarization means more negative inside here, or more negative here than outside. So it's more negative here, it's more positive outside. More negative inside, more positive outside. Now, when we want to depolarize this membrane, what are we going to do? We are going to change the orientation. So it will now become less negative outside. Less negative inside, right? If polarization is more negative inside, then depolarization will be more positive inside. Does that make sense? It's just going to be opposite of the initial. So when this portion is becoming less negative, then that will be depolarization. All right. Now, I will still talk about that as we go. Now, so the transmembrane, we are looking at the characteristics of graded potential now, which is a stimulus that is not enough to fire an action potential. So the transmembrane potential is most affected at the site of the stimulation, the site where the stimulus is there. And then the effect decreases with distance. You see that? So on the image I showed you, we had 65, negative 60, negative 65, negative 70. So the impact is reducing as it goes. So that is not action potential, that is graded potential. When the impact of a stimulus is reducing and not circulating, that is action potential. You see, the effect spread passively. It's not active, owing to local current because it's localized. The graded change in the membrane potential may involve either depolarization, meaning that the membrane becomes more positive inside than it was negative before, or less negative than it was, or hyperpolarization, which means more negative. you know, normally it's negative 70. So if it goes to negative 75, if it goes to negative 80, that is hyperpolarization. Depolarization will be that it's now becoming negative 60, negative 60, negative 55, negative 40, negative 20. That's depolarization. So depolarization will be like, this will be like depolarization now. Negative 40 will be depolarization. Up to positive 30 will be depolarization. Hyperpolarization will be up to negative 75. That's hyperpolarization. And it can go up to negative 90. That will be hyperpolarization. All right. Now, for example, in a resting membrane potential, the opening, see, look at this statement, the opening of sodium channel will cause depolarization. Now, I told you that sodium channel brings sodium channel will, you know, there are two channels, the potassium channel and the sodium channel. I told you that sodium channel brings sodium into the cell, right? So when the sodium channel are open, it will, in quote, unpolarize the membrane because more positive is now coming in, right? So this inside the cell is going to become more positive and less negative. Does that make sense? So initially, the cell was initially polarized. What will make it become depolarized is when it is losing its negativity. All right. If more sodium comes in now, sodium is positive charge. So if more sodium is coming in, more positive is coming into the cell, and the cell become more depolarized. All right. Now, on the other hand, opening of potassium channel. Now, we know that potassium channel, once it opens, what direction is potassium going? Potassium is going out. All right. If potassium channel open, potassium is going out. So the cell is going to be becoming more negative because potassium is going out of the cell. And potassium has the power to push a cell to become up to negative 90. So polarization can happen, then hyperpolarization can now happen. Whereas sodium will open up and bring sodium into the cell. Positive charges coming into the cell is going to become more positive. Okay, so depolarization simply means the cell becoming more positive inside. Hyperpolarization means the cell becoming more negative than its rest membrane potential inside. All right. Now, that is, the change in membrane potential reflects whether positive charges enter or leave. And again, looking at those two channels, I'm not talking of sodium potassium pump now. I'm talking of those sodium channel and potassium channel separately. Sodium channel brings sodium into the cell. Potassium channel make potassium to go outside of the cell. So take note of that. Sodium channel brings sodium into the cell. Potassium channel takes potassium outside of the cell. Now, the fourth point here, the stronger the stimulus, the greater is the change in the transmembrane potential, and the larger is the affected area. Smaller the stimulus, the smaller is the change in the transmembrane potential, and the lower, the smaller is the area that is affected. All right, now let's go. So we want to look at action potential now. I will start with this image here, then we'll go ahead and look at the story. Action potential. In the event when the stimulus is enough to generate an action potential, what happens? That's what we want to look at now. I'll be rounding off this section fast quickly so that we can possibly take a break. Now, what happens when when the stimulus is enough to generate an action potential? So at rest, we have this. At rest, we have negative 70 millivolts. That is when the neuron is at rest. And I told you that is a state of rest when the cell is said to be polarized. And polarization means that the cell is more negative inside. Like you can see this, we have more negative in the inside of the cell than what we have on the outside. So the cell is more negative inside than the outside. Now, stimulus is applied. The moment stimulus is applied in step 1, what do you notice? The resting membrane potential is no longer at rest, or the membrane is no longer at rest. It has reached negative 60, and negative 60 is threshold. Once the threshold is reached, what is going to happen at that point? What will happen is that this, you see the sodium channel, the sodium leak channel is going to open. When the sodium leak channels, you see activation of the sodium channel. Once the sodium channel opens, what's going to happen? A lot of sodium ion go into the cell. When sodium ion goes into the cell, this channel is open. When the sodium ion channel goes into the cell, what's going to happen? You see the cell has become positive 10 at this point, and sodium have the capacity to move a cell from negative whatever it is to positive 30, right? Now, immediately that this cell has become depolarized, which means it is now positive inside than what is outside. Now, the moment that happened that the cell has become positive inside, the cell was initially negative 70. Now it's positive 60. Now that tells that the cell has been fully depolarized. Then the system says, okay, this cell has been depolarized. We need to stop it now. Then you also want to take note. When you want to stop your car, what's the first thing you do? You stop matching the accelerator. But the moment you stop matching the accelerator, is the car going to stop straight? No. The car reduces in speed. So the speed of depolarization is going to reduce because sodium ion channel now closes. As the sodium ion channel is closing, but it's not going to randomly stop because you remove your leg from the accelerator. No. The car is still going to keep speeding, and that will happen, and the cell will get up to positive 30. Even though the system has inactivated sodium channel, but the sodium channel is going to push it up a little bit, just like your car will continue to move a little bit. Now, the next thing that will happen to stop your car is that you match the brake actively. You remove your leg from the accelerator and match the brake. Now, matching the brake is to activate potassium channel. So potassium channel is going to be activated. Once potassium channel is activated, what's going to happen? Potassium begins to leave the cell. See, so here is what you see. Potassium begins to leave the cell. Potassium begins to leave the cell. When potassium is leaving the cell, what is the ability of potassium? Potassium have the capacity to push a cell from whatever it is to negative 90. Now see what's going to happen. Now the cell is now in step 4, is now in negative 90. Now, before it gets to this negative 90, it's going to get to negative 70. And when it gets to negative 70, again, the potassium channel also will be inactivated and say, okay, now let's close this channel. But in between the process, gradually, because it closes gradually, it will still push the cell up to negative 90. Now, as they put the cell up to negative 90, then the sodium potassium pump now sets in to balance the cell by sending out 2 potassium, bringing in 3 sodium. Sending out 2 potassium, bringing in 2 sodium. Now, let's go ahead and look at the story, and it will make more sense to you. Now, number 1 is that number 1, depolarization will happen. How will depolarization happen to the threshold? It's the stimulus initiate that, bringing the cell from its negative 70 to negative 60, which is the threshold. At this threshold, action potential must happen. Either the system likes it or not. Once the threshold is achieved, action potential will happen. Now, once this threshold is reached, what's going to happen? Sodium channel is going to open. When sodium channel opens, what's the purpose of sodium channel? It has the ability to drive a neuron from wherever it is to positive 30 millivolts. So sodium channel is going to open, and sodium is going to go into the cell, and then it flood into the cell, change the membrane from negative 60, the threshold, to positive 30. Now, as it gets to that, somewhere around positive 10, it starts to close. But as it's closing, inactivating the system, the sodium channel, sodium is still going to flush in and push the cell to positive 30 millivolts. At that time, immediately, potassium channel is going to open. The cell is saying, I am hyperpolarized. I'm depolarized now. In fact, I am too much depolarized, up to positive 30. This is too much for me. Then the system says, now let's help the cell, the neuron, by activating the potassium channel so that we can bring the cell back to its resting membrane potential so that the cell can rest. Then the Once the potassium channel is open, then potassium begins to go out of the cell. So you see, potassium diffuse out of the cell. And what is going to happen? The cell is now going back gradually to its resting stage. And potassium is also not too nice. It will push this cell from the rest and take it to become negative 90 again. And now, so the voltage gated channel regained their normal properties about 0.4 to 1.0 millisecond. The membrane is now capable of generating another potential. I'll talk about that. If a larger potential stimulus is added, the voltage gated channel begins closing at negative 70. You see that? Because they do not all close at the same time. You see that? Potassium loss continue and temporary hyperpolarization is going to happen. Now, what is going to happen at the end of the relative refractory period, which I'll talk about? All voltage gated channel have closed and the plasma membrane is back to its resting state. All right. All right. So looking at this now, we've discussed how action potential actually happen. Then I will quickly just touch base on few things before I round off. I will let you read some part of it yourself since I've explained it majorly. Now, how does the cells, if action potential has happened, we talked about the cell becoming polarized, becoming depolarized, and also the cell needs to be repolarized, all right? And for repolarization, we said that to go back to its negative state that it was, another channel has to open, and that is the potassium gated channel that we talked about. And then potassium is going to flow out of the cell. Then the cell is going to now become negative 70. And then by the time the potassium channel is closed, it will still push out some potassium more up to the point that the cell becomes hyperpolarized, which is what we call negative 90 millivolts, because that's the power, the ultimate power of potassium. It can push a cell to become negative 90 millivolts. Now, after that has done, potassium channel has done its job, then sodium potassium pump is going to set in so that it can restore the resting membrane potential to negative 70 millivolts. And I told you that this happened, that sodium potassium pump out 3 sodium. So 3 sodium goes out and 2 potassium is going to come into the cell. And that's how the balancing is done. So in quote, the cell will be losing every transaction. Now, at this point, we are not concerned about the concentration of what is coming in, either it is sodium or potassium. We are concerned about the fact that 3 positive charges are going out and 2 positive charges are coming in. That is what we are concerned about. We are not concerned about the chemical gradient. We are concerned about the electrical gradient. All right. So in any of this process, there is nothing that is special about. Our focus is not in the chemical gradient, if it is potassium or calcium or sodium. That's not our emphasis. Our emphasis is in that a positive is going out, positive is coming in. So electric current is our concern, not chemical gradient. Electric gradient, not chemical gradient. All right. So if you look at this pump now, how will this get back to negative 70 millivolts? The way it's going to get back to negative 70 millivolts is that 3 sodium is going out. So if every time 3 sodium is going out, 2 potassium is restored, it means at every time the cell is losing 1 positive charge every time. So every time 3 sodium goes out, 2 potassium is coming out. So think about it, 3 positive goes out, 2 positive comes back. So the cell is losing 1 positive every time. And that's what is going to bring the cell from negative 70 to negative, from negative 90 rather, to negative 70. By the time the cell keep losing 1 sodium every time, right? All right, so that's how sodium potassium pump helps to maintain or restore the membrane potential. So this is just a little chart to show you how repolarization is on the chart. So again, look at this. Chemical stimulus is applied here. This is at rest. Stimulus is applied here. Then the cell is going to become depolarized. All right. The cell becomes depolarized, become a little more negative. This did not push it up to threshold. So this is like, let's say 65. So it's localized. All right. So this happen here. Then it go back to normal again, repolarization. This just showing you how that works. Then hyperpolarization, and then restored again. All right. Now, this is very, very interesting, and I want you to pay very close attention to look at this as I begin to round up. There's something we call refractive period. Refractive period is a time when the cell, the neuron, cannot generate action potential. What does it mean to generate action potential? It means to respond to a stimulus. So that means there's a point in your cell, in your neuronal activity, that the neurons cannot generate action potential. The neuron cannot respond to stimulus. Why does that happen? Now, there is a point. Think about it in this scenario before I go to the next slide that shows you the image. Think about it. If I step on a nail now, I'm not going to step on a nail, but let's say I step on a nail. Nail and needle, which one is bigger? A nail is bigger than a needle. So a nail will hurt me more than a needle will hurt me. So let's say I step on a nail now, and I'm just feeling that pain. Then I step on a needle. I'm not going to feel any pain from a needle because I am still responding to a nail. So let's say that somebody touched an hot stove, and then hot rice spill on that person on that same spot. Nothing is going to happen because the pain of touching the stove is more than the pain of rice, like warm rice or hot rice that is already outside of pot, hurting you. That is not going to generate anything. So now there's a point in between the process that the cell cannot respond to any action potential. So after an action potential begins, neuron cannot generate another action potential. Now, these are two types. Refractive period have two types. One is the absolute. Absolute means absolutely nothing will happen. So at this point, sodium channel activation and inactivation has happened. At this point, what happened is this. Once the sodium channel is activated, right, that is what leads to depolarization. As the cell is being depolarized, the moment that channel closes, it will not open again. It will not open again until the process finishes. At that point, we call it absolute refractive period. So inactivated sodium channel cannot reopen. And if sodium channel cannot reopen, that means the membrane cannot depolarize again because it's currently depolarizing. All right. So that means the depolarization cannot overlap on each other. So it must return to its resting stage before it will generate another action potential. Now, there's another kind of refractive period that is called relative. Now, the relative is this. Reverse the scenario I used earlier. Let's say a needle, I step on a needle, then I step on a nail. Now, I'm going to forget the needle because the needle is nothing compared to the nail. I'm going to forget that I step on a needle because a different action potential that is greater stimulus has been applied. So a greater action potential will be generated. So look at it. Second action potential can be produced if a larger than normal stimulus is supplied. Now, voltage-gated potassium channels still open after inactivated sodium ion channel are again at their rest. Now, look at what I'm saying on this chart here. This is what we are talking about. I will use this to illustrate the general action potential. Then I think I'll be stopping here. Every other thing, there are things that are applications based on what we already studied. All right. Now, this is the threshold. This is the resting membrane potential. Stimulus are applied, brought the neuron to the threshold. Threshold is reached. action potential must happen. Sodium ion channel opens, and the sodium ion begins to flush into the cell. A lot of sodium goes in. A lot of sodium is going in, then push the cell to to positive 30 millivolts. Then it has reached the peak. Then sodium channel was closed, potassium channel opens up, and then return. Repolarization means to restore depolarization, restore it to the resting membrane potential. So the resting membrane potential is being reached here now. And then sodium will always, potassium will always do more than normal, right? Always push it to its own state, to its own potential, which is negative 90. So it pushes the membrane up to negative 90. That is that. At that point, the potassium pump is going to close. When potassium pump closes, what's going to happen? Sodium potassium pump is going to open and then restore the membrane to its negative 70 millivolts. That is all about all we have discussed. Now, at this point, between this point when the sodium channel is open, all right, between these two terminals is the point where we call the absolute refractive period. At this point, there's nothing that will happen that will cause the neuron to generate another action potential. And the point where we call relative refractive period is this point when the potassium ion is open here, potassium ion channel is open here. At this point, if any stimulus comes in, the cell will respond to that. So it will respond to a larger stimulus at this point. But here, there will be no stimulus that will be responded to. But here, for there to be any action potential here, it has to be a larger stimulus than the ongoing one. All right? That is that. So I'm going to stop at this point.